the concept of steric number is going to be what's going to tell you whether an atom is sp3, sp2, or sp most of the time. Sometimes there will be exceptions, but they're very special cases, and we'll see why, but probably not until next semester for the most part. Okay, so valence shell VSEPR theory is what tells us all about the shape, and we can use this combined with what we just saw in hybrid orbitals to come up with this. The way we figure out the steric number is a very simple formula. It is, you look at an atom and you say, how many sigma bonds is the atom making? Plus, how many lone pairs does that atom have? What's another way of saying number of sigma bonds? Instead of saying number of sigma bonds, you could also say to this carbon, how many atoms is it bonded to? Okay, so this carbon is bonded to 4 atoms. We don't count pi or pi bonds. We're just, how many different atoms is it bonded to? It's bonded to 4, and it has no lone pair, and you add that up, and you get 4. The nitrogen here, it's only making 3 sigma bonds. Remember, every single bond is always a sigma bond. Okay, a single bond is always a sigma bond. But it also has 1 lone pair, and that needs to take up space. So 3 plus 1 would give us a steric number of 4. And as we already saw with water, there's 2 sigma bonds and 2 lone pairs, steric number of 4 for all of those. Okay. Knowing that number tells you something very important. And if you remember from Chem 120 and Chem 130, that's going to tell you the shape for the most part. These 2 numbers tell you the shape. We called this tetrahedral. What kind of a shape did we call this? 3 atoms, 1 lone pair. Do you remember?
Trigonal planar?
Trigonal
Planar.
pyramid. Trigonal pyramid. Okay? Yeah, it's trigonal planar when there's no lone pair. But when there's a lone pair, that's called trigonal pyramid. For example, if I were to really quickly build a little model here, trigonal pyramid. Looks like this. All right, looks like this, but it's not flat. You'll notice the blue pokes up straight out of my hand. And up here is a lone pair. Okay. And then what is this shape called? There's a number of different names for this one. It's not linear. Okay.
Bent.
It's bent or V-shaped or angular. Yeah, I like bent. Bent is fine. Okay. What are the approximate bond angles in all of these? Approximate. What is it in this one?
It's 109.
109.5, yeah. These are all about 109.5. So this one is 109.5. Ammonia is about 107. Water, I think, is 104.5. So they're all very close to 109.5. Okay. So to predict which hybridization you use, you get that from the steric number. If the steric number is 4, it will be sp3 hybridized. If the steric number is 3, the atom will be sp2. And the steric number is 2, then it's sp. This is like a big question, like on my first exam. I mean, you know, this is like 8 to 10 points. I'll give you a molecule and say, find every atom and label it sp3, sp2, or sp. You know, that's very important. So it really just comes down to that steric number. So, for example, if we look at ethane here, what is the steric number of that carbon? How many sigma bonds is that carbon making?
2. Oh, three.
Yeah. So it's 3 sigma bonds and a pi bond, right? So only the sigma bonds, 3. And how many lone pairs does carbon have?
0.
0. So steric number of 3 means it should be sp2.
Oh.
Yeah. And then finally, going into my notes again, acetylene. This carbon is bonded to 2 atoms. That means it's making 2 sigma bonds, right? And it has no lone pairs. And so therefore it has a steric number of 2, which means it is
SP.
sp. Good. What shape is associated with sp? No. These are 180-degree angles. These are linear. Okay. So when we think of sp3, sp3s are typically tetrahedral. Okay. And there's 3 different shapes in the sp3 family. Pure tetrahedral. We don't use the word pure really, but I would call this pure tetrahedral because it's only bonded to atoms. This is called trigonal pyramid. And this is bent, as we said before. What does the lone pair do to the bond angles? Remember, these are normally 109.5, but in ammonia, it's close to 107. So what does that imply the lone pairs are doing? And look at the trend here. It gets even smaller over here. Lone pairs take up more space than bonded atoms usually. Okay. And so what that means is it pushes the bond angles to smaller values. So whenever there's lone pairs, they make the bond angles smaller. If for some reason this was bonded to a very, very large atom, like iodine, that would also push the bond angles together. Anything that takes up a lot of space pushes the other angles together. So the sp3s are summarized on table 1.3. So again, the names of the shapes or the geometries are tetrahedral, trigonal pyramidal, and bent. As I mentioned before, some people get really upset and say, no, that's not really sp2. I mean sp3, but it's easier just to accept it and smile. sp3, whether it really, really is or isn't a big issue. It's the only way we can explain the bond angles, though. Boron trifluoride. If we look at the boron here, how many sigma bonds is it making?
3.
3. And how many lone pairs does boron have?
0.
3.
0. So its steric number is
3.
3. And steric number of 3 means sp2.
Yes.
Good. And so the general shape is called trigonal planar. And when it's exactly that, the molecular geometry is the same as the shape. It's called trigonal planar, the electron shape. So that means it's flat. It lies in a plane at 120-degree angles there. That again should be kind of a review. We talked about that in 120 and 130. All right. How many electrons are in boron's p orbital? This is important. How many valence electrons does boron have? If you look at the periodic table, I don't know that I have one sitting here right now. Yeah, there's boron right there. How many valence electrons does boron have?
3.
3. Good. And so it's using each of those electrons to make a bond to fluorine, right? So if it has 3 and it's using one to make a fluorine here, one to bond with the fluorine here, one there, then how many electrons are left to put into the p orbital? It's using one here, one here, one here, so there are, very important, none left over. The p orbital is empty. It is vacant. That's going to be very important for understanding how boron reacts. This is a very unstable compound. If it was hydrogens, it would also be very unstable. Why is this a very unstable compound? What about it seems wrong?
Lone pairs on fluorine.
What's that?
Is it the lone pairs on fluorine?
The lone pairs on fluorine. Forget it for a second and change them to hydrogens. Pretend they're hydrogens. Okay? That would be called borane. It's still very unstable.
Octet rule.
Octet rule, yeah. Boron is a terminally unhappy element. It's the real miserable element in that it always wants an octet, but as soon as someone comes along to give it its electrons, it gets a negative formal charge and it's unhappy again. So it's very useful because you can get it to make bonds, then lose bonds, then make bonds, then lose bonds, then make bonds. And that means you can get it to carry out lots of different reactions. So boron comes up in a number of places in the class because of the fact that it doesn't have an octet. And it's always going to be able to migrate from one kind of a structure to another. We say it's also what is called a Lewis acid. Do you remember what Lewis acid means? Probably not. Lewis acid means electron pair acceptor. It goes looking for electron pairs. Good. Okay, this kind of a structure is called an imine, I-M-I-N-E. We will talk about them next semester, but let's look at it right now. What is the steric number?
Is it 4?
So the nitrogen has how many sigma bonds?
3? No, 2. Oh,
2.
2.
Lone pairs?
1.
1.
1. So steric number is
3.
3. Good. So that means we predict what hybridization?
sp2.
sp2. Good. We predict sp2. And what's the shape of that? Anyone know? That's the other one that's called bent. Bent. It's called bent. Okay. So this shape is called trigonal planar. And this shape, meaning you have 2 sigma bonds and a lone pair, is called bent. Or angular, sorry, bent or angular. We already saw the term bent used up here. Sorry. With water. So there's 2 different ways a molecule can be bent. It can have 2 atoms and 2 lone pairs, or it can have 2 atoms and 1 lone pair. But what is different? Even though they're both called bent, the bond angle is closer to 109.5 with sp3, but with sp2, the bond angle is closer to 120, right? Okay. And then finally, let's look at a couple more cases here. Beryllium hydride and carbon dioxide. So beryllium hydride, beryllium has 2 valence electrons only. It's in group 2. We don't talk much about beryllium. Hydrogen has only 1, which means it would make sense if each one brought 1 electron. So we'll change that to the following. So beryllium hydride, what would we predict here? Steric number should be how many pi bonds?
2.
2. How many lone pairs?
0.
0. So the steric number is 2. That means if it is hybridized, we would expect it to be sp, right?
Yes.
A lot of people would argue with me on that one, but fine. According to hybridization, it should be sp. What would the angle be? SPs are always what angle?
Linear.
Yeah, they're linear shapes, so they're 180. Yeah. So SPs are always linear. And that's the only shape we have for SP, linear. Carbon dioxide, carbon makes 4 bonds, right? So carbon with 2 oxygens, 2 bonds to oxygen there, 2 bonds to oxygen there. And remember, we're only looking at the carbon. How many sigma bonds is it making?
2.
2 sigma bonds plus 2 pi bonds, but we don't worry about the pi bonds for right now. And then how many lone pairs on carbon?
0.
0.
Yeah, so no lone pairs. And so therefore it would be steric number is 2. Good. So it's SP, which means again, we expect it to be
Indeed.
linear.
180.
Yeah, with 180-degree angles. This is a rather uncommon bonding pattern. Carbon making 2 double bonds. There's only a few important molecules that do that. Carbon dioxide being by far the most important. By the way, carbon dioxide is not considered organic, even though it has carbon. Usually that's because what element is it also missing? What element should it also have to be organic?
Hydrogen.
Hydrogen, yeah. Usually if carbon doesn't have a hydrogen, we don't call it organic. That's not a test question or anything important. It's just classification. I don't know why people do that, but that's what they do. All right, so all of this is ultimately summarized on table 1.3. And this figure comes from the book. So if this is not familiar, you don't remember it, it's all in the book. Just remember sp3s are about 109.5 bond angles, sp2s are about 120, and sps should be 180 degrees. Be very, very careful not to mix up bent and linear. Okay. The book goes way too much in depth on the next subject than I like to. It's not that I don't like math, as any of you who had me for 140 knows I love math, but it's just too much detail here. Polarity, we already talked about bond polarity, right? And it's all based on difference in what between 2 atoms? The difference in
Electronegativity.
Electronegativity, yeah. Oh, yeah, I've got it right there. Right. Okay. Electronegativity differences cause induction. Induction means it's pulling electrons toward it. We're going to use that induction argument a lot when we talk about acids and bases, especially acids in chapter 3. But just understand electron means, think of it as electron vacuum cleaner, means sucking electrons toward it. Okay. Now, the dipole moment tells us where the electrons want to go overall in a molecule. Okay. And there is a mathematical formula for this. It's relatively easy to do when you have only 2 atoms. Beyond that, it gets much more complicated. So dipole units are measured generally in units of Debye, And we can use these to come up with a quantitative number. Using calculations here, we can ultimately calculate the value of a dipole moment as the amount of charge times the distance. And then using this formula, we can calculate the amount in divisors. As I say in the notes, I'm not going to ask any calculations for this. The only thing I want you to understand is the bigger that number, the bigger the dipole moment, the more electrons are being pulled towards one atom or another. Okay, so if it's 2.30, that means the electrons are really being pulled in a certain direction. They're being pulled out in a different way. So if we looked at some examples here, again, I'm only interested in, I just want you to be able to look at these numbers and compare them. Okay, so carbon oxygen single bond is 0.7 dBi. That's pretty significant. But oddly enough, compared to an oxygen double bond, it's not nearly the same here. A much, much bigger dipole moment. What is the key difference between these? What is the biggest difference between them ultimately? Two things. Shorter bond length, right? Double bonds are shorter because they're using sp2 orbitals. Shorter bond length means smaller number in the denominator, means bigger number overall. Okay. And ultimately, there's two bonds to the oxygen, which means twice as much charge. So you don't need to worry again where the numbers are coming from, but just that this is a much bigger number. So the electrons are being pulled much more towards oxygen than carbon. This is going to have a very big effect on reactivity. Things with electrons that want to donate electrons are going to be really interested in carbons on double bonds. Why? Because where are carbons electrons being pulled? They're all being sucked away towards the oxygen. The electrons on this carbon are still being sucked away towards oxygen, but it's by a smaller amount. Okay, so this is just a way of quantitating them. In addition to having these values, these are also going to have direction. What do we call that in physics? Something which has a number and a direction, a quantity that has both.
Vector.
Vector.
Yeah, it's a vector. And the vector totally depends on which way you draw the chlorine. If you drew the chlorine to the right, the vector would have to point towards that. Okay. In this class, we're just going to settle with doing approximate drawings. And in general, you draw your dipole moments towards the most electronegative atoms. If there are two or more of them, they add up together. And after a while, it gets even more complicated than that. You can use software to predict it. Okay. So this molecule is rather important. This is called dichloromethane. We take two of the hydrogens and change them to chlorines. If you add up the two dipole moments for each bond, they combine to form one that goes right between the chlorines. So this means essentially the electrons are being pulled this way. If we did all the math on it, we would find this is not extremely polar. Okay, fairly polar, but not extremely. It's about moderate. Ammonia and water, on the other hand, are more polar. And in both of these cases, the electrons are being pulled towards the oxygen or the nitrogen. Okay. Much more interesting to us as organic chemists recently, over the past 20 years or so, is we have come up with a technique of representing these with surfaces. And the surfaces essentially tell us where the electrons want to spend most of their time. More negative is red. The most positive is blue, with green standing for the most neutral. That's going to be very important because this will be one of the first molecules we look at the reactions of. If this is very positive, that means what kind of molecule is going to come chasing that carbon? Something which is going to be very negative. Like, for example, hydroxide, OH minus. That oxygen has an extra lone pair, and we go, I would love to give that lone pair to this carbon, and it does that. It throws its lone pair at carbon, and this chlorine abandons it. It's called a leaving group. It just goes the other way and makes methanol. So that'll be one of our first reactions. So knowing where we have our positives and our negatives is fairly important. I realize I skipped a slide. Okay, sorry about that. So when you're trying to generally predict a molecule's geometry, you want to look at the geometry before you do the polarity to see if groups are going to cancel out. Let's go back to carbon dioxide for a second. Are the carbon-oxygen bonds polar or non-polar? We've already seen this before.
Polar.
They're definitely polar, but is carbon dioxide polar or non-polar overall?
Non-polar.
Non, because the electrons want to go in
Opposite
directions. And whenever the electrons are being pulled in totally opposite directions, the molecule as a whole has no dipole moment. Okay. We will find cases where molecules will want to attack that carbon because the electrons are being pulled to the different sizes. If I was to take this molecule and do one of those color codings on it, what color would be around the oxygens?
Red.
Red, good. And, we can actually do this. Just by drawing this really quickly. chemmagic.org. Oops, local storage. Okay, good. If I want to just draw carbon dioxide, that's a relatively easy thing for me to do. Boom. Let's change those to double bonds. Definitely not the right shape. So there's carbon dioxide with carbon in the middle. And I'm going to go ahead and ask it to calculate the MEP. And there we see it's very red on the edge of each molecule. So it means the electrons are really liking to hang out over there and over here. And very blue in the middle, which means electron deprived. Okay. These atoms are all neutral. That means they have no formal charge, right? But if we want to look more detailed, we could actually ask it, well, does it really not have any charge? And you see, actually, what is it telling me? The carbon really is almost like it has a positive charge, and the oxygens are almost like having a negative. That's not something you'll need to do. This is all more advanced stuff, but the idea is important. Even though the formal charge is 0, in reality, it's pretty positive, which means something which is negative would be attracted to that carbon. Okay, so these diagrams really help. They tell you, where attractions are going to be. Blue is attracted to red. The blue of one molecule will be attracted to the red of another, because blue is positive, red is negative. Okay. Table 1.5 gives some different molecules here. Let's take a look at some of these. Which of these, according to this diagram, has the biggest dipole moment?
Acetone.
Yeah. But oddly enough, it's not really the most polar molecule here. By far, the most polar molecule here is water. So dipole moment is part of it, but size also makes a difference. Water is much smaller, so it's much more concentrated in a small area. This is, again, why I usually don't like to talk about dipole moment. I find it much more confusing for people than it's worth. Just direction. Pentane. Why does it have a dipole moment of 0? A couple of reasons. What would be one that you might think of?
Carbon is neutral, electronegatively neutral.
Yeah, so all the carbon-carbon bonds have 0 dipole moment. Carbon-hydrogen, remember, we said carbon and hydrogen pretty much share almost equally, right? On top of it, this whole molecule is symmetrical. I can cut it right down the middle in all ways. So if there even were a dipole, it would totally cancel. So that means pentane, do you think it's going to want to mix well with water, if you were to just guess?
Nope.
It's not, yeah. Things that are very dissimilar like this usually don't want to mix very well, okay? Pentane is much more likely to mix well with carbon tetrachloride below it, okay? Now, you will need to know the relative polarity of some compounds, and that we will talk about in lab on Monday. And there'll be a whole list of very common compounds, including acetone, water, methanol, ethanol, methylene chloride, ether, all of these. They come up a lot. And so it will be important, but it won't be based only on the dipole moment. There'll be other things that come into it. Okay. The last really big topic is intermolecular forces. I'm going to go through this fairly quickly because we covered it in 120 and we cover it in 130. I know it might be fairly far away, but I'm hoping you remember this stuff, and it is very important. As far as when we look at properties of different compounds, one of the most important things to always consider is intermolecular forces, and it's critical for biological functions as well. So when we talk about how soluble chemicals are, that's our first lab, solubility. What temperature does something boil at? How dense is it? All of these questions largely come up to not bonds, but the attractions between different molecules. So instead of the attractions between atoms, it's the attraction between atoms of different molecules. And those are the intermolecular forces. There are 3 that are of very important terminologies here. Dipole-dipole, hydrogen bonding, which is going to be by far our most interesting, and dispersion forces, also called London dispersion forces, also called van der Waals forces, but dispersion, I'll just call them usually London forces or dispersion forces. Okay. And they are going to have different strengths as far as this goes. Dipole-dipole are the easiest to understand. Dipole-dipole forces just say when one molecule has a dipole, it's going to be attracted to another molecule with a dipole, with the positive part of one molecule being attracted to the negative part of another one. Okay. So look at acetone here. Oxygen's the electronegative part. What color do we give it? We give it a nice red, right? If the electrons are being pulled towards the oxygen, then who's being deprived? The carbons and the oxygens, right? I mean, the carbons and the hydrogens here. So electrons are being very strongly pulled towards that oxygen, so this area is positive. So if I put a bunch of acetone molecules together, they're going to try to attract each other like this, with the negative of the oxygen attracted to the positive of this carbon. And this pattern continues on and on and on. If we were to freeze acetone, acetone's normally a liquid, but if you were to freeze it, they would try to line up this way. This would be the most stable orientation, would be to have positive next to negative. We say that this dipole moment is permanent. Why? Because oxygen is always more electronegative than carbon, right? It's never going to change on you. Oxygen is always more electronegative than carbon. That's called a permanent dipole moment. Okay. So what do you think this does? Having this force, does that increase the boiling point and the melting point or lower it, as opposed to if you didn't have this force? If everything here was neutral, does this make these molecules easier or harder to separate?
Harder to separate.
Harder. Yeah, it's like magnets, right? The more attached to each other, the harder they are to separate. So that means it does what to the boiling point? That's the energy you need to separate them. It makes the boiling point go up. Melting point usually follows the same trend as boiling point. Melting point can be a little more complicated, but they generally follow the same trends, okay? So the stronger the attractions are, the more energy is needed to separate molecules, therefore higher boiling point, higher melting point to separate them. Okay. So compare these two compounds and you see a huge difference. Acetone does have a dipole moment. Is there a dipole moment here? A significant one anyway.
No.
No, they're all carbons, right? So they should be sharing pretty much equally. So there's no positives, no negatives, no partial positives, no negatives. If everything is neutral, then how are these going to attract each other? And the answer is, not very strongly. So the melting point and the boiling point is very low. Acetone, on the other hand, still kind of low, but nowhere near as low as isobutylene. What is acetone at room temperature based on these here? Based on these, assuming room temperature is 25 Celsius, is it a gas, liquid, or a solid?
Liquid.
Good. 25 degrees is between the melting point and the boiling point. Above the boiling point, it would be a gas. Below the melting point, it would be a solid. So it's in the middle. It's a gas. Isobutylene is what at room temperature?
Gas.
It's a gas. Yeah. Because 25 degrees is higher than the boiling point. So at room temperature, it's already boiled, we could say. It's a gas. Hydrogen bonding, probably the most important, is just a very extreme type of dipole-dipole force. So it is technically a dipole-dipole force. It occurs between hydrogen atoms bonded to phone, F-O or N, phone, F-O or N. And by far, oxygen and nitrogen are more important than fluorine. We won't deal with fluorine a lot. It does come up though. Oxygen, this bond has such a strong dipole moment, the electrons are being pulled so much from this oxygen, and this hydrogen is so small that it's like a bundle of positive charge. Same thing with these lone pairs on this oxygen. Okay. So there is a rather strong attraction between these. Same thing here. So the way I talk about this in Chem 120 is to say, where is it? Okay, so the attraction is between a hydrogen on the phone. You need two pieces. So a hydrogen on the phone, which would be hydrogen on F, O, or N. I'm leaving out the lone pairs here. Oops, sorry. Put the lone pairs in now. And some other phone. So for example, The only requirement of the other phone is that it have a lone pair somewhere. So usually they are different molecules. Sometimes they can be the same molecule if it's a big molecule, and it's like the head of the molecule attacking the tail of another molecule. We'll see examples of those later. So there's no rule that says that it has to be the same type. So this hydrogen would be attracted to this fluorine, or it would be attracted to an oxygen or a nitrogen. Same thing with this hydrogen. It could be attracted to that fluorine, could be attracted to that oxygen, could be attracted to that nitrogen. Same thing here. Very important. What kind of bond are these that I'm pointing out right here? Are those hydrogen bonds?
No.
No, those are what kind of bonds?
Covalent.
These are covalent bonds. Good. The hydrogen bond is not a bond. That's why I hate the term hydrogen bond. It's not a bond. It's an intermolecular attraction. Yeah, good. It's an intermolecular attraction. So I'd like to remind everybody, it's like an English horn. An English horn is not English, and it is not a horn, okay? It's a French big oboe, but I wasn't the one who named it. So, you know, that's what they call it, hydrogen bonding, and we just have to deal with it. Okay. And those are the only atoms, fluorine, oxygen, nitrogen. Some people will try to argue chlorine too, but just swap them down, say, no, no, no. Only fluorine, oxygen, nitrogen. Okay. Chlorine's kind of on the fence. Okay. It almost can hydrogen bond, but it's not quite in the club yet. Okay. So even though they are very strong, they're about 20 times weaker than covalent bonds. So that means not a bond, not really a bond. Okay. I will use this word a lot, protic, protic. Any hydrogen, any compound that has a hydrogen that can hydrogen bond is called protic, especially if it's a small molecule. This compound here is ethanol. It's protic because it's got a hydrogen on an oxygen. Ammonia is protic because it has hydrogens on nitrogen. So wherever we have a hydrogen on oxygen, that's protic. So these are four very important solvents. Which of these is protic?
Acetic acid and dimethyl sulfoxide.
Acetic acid is definitely protic because it's got the OH. Dimethyl sulfoxide is not. We call this aprotic, which is the opposite. The hydrogens are all bonded to what? Carbon, right? Okay. Here, the hydrogens are all bonded to carbon, so it's aprotic. Diethyl ether also is aprotic. It only has part of it. If I put diethyl ether in water, some of the waters will be attracted, but not much, because the attraction only goes one way, the oxygen to the hydrogens. There's no hydrogens on oxygen. So remember, that's what you're looking for, hydrogen on oxygen or nitrogen, and sometimes fluorine. Are we all okay with this? Does this make sense? Take a look at all three of these. Are these all three protic?
I have a quick question.
Okay. Yeah.
So what you're trying to say is that protic, are we looking at it as like that we can bond it with something else?
It can be, all it means is it can hydrogen bond.
Oh, it can hydrogen bond.
And it has the well, technically it means it's not only can it hydrogen bond, it has to have hydrogen on F, O, or N on it, okay? So it has to have an OH bond or an NH bond, okay? The reason I don't bring up fluorine is because there's only one chemical that has fluorine hydrogen, and that's this one. Hydrofluoric acid, which is not really a solvent, unless you're playing Breaking Bad and are trying to dissolve bodies, you know, but we're not going to do that. Okay, horribly nasty stuff. Anyway, so this does have an oxygen, but none of the oxygens have hydrogens on it. Same thing here. This has hydrogens, but no OH. You're looking for OH or NH. All right. So triethylamine does not have, all the hydrogens are on carbons, right? No hydrogens on nitrogen. So what seems to be the trend here? Why does propylamine have the highest boiling point and trimethylamine the lowest? What seems to be the difference?
It has more hydrogen bonds.
Yeah, propylamine has 2 hydrogens. Which can hydrogen bond, right? That means more attractions. That means most attractions. Because what could I do with each of these hydrogens? I could draw another propylamine
Yeah. Oh, it's
being
really
attracted on each hydrogen. Each hydrogen would have another propylamine attracted to it. Okay. Ethylamine only has 1 hydrogen, so it could only be attracted to one other ethylamine with the hydrogen. But the nitrogen could be used to attract another one too. So technically, the lone pair can attract and the hydrogens can attract. So we could get as many as 3 attractions here. Here we can only get 2. Triethylamine can't hydrogen bond at all, okay? There are no hydrogen atoms bonded to F, O, or N. And N is all that matters here. And again, hydrogen bonds means attractions, higher boiling points.
I have a quick question.
Yeah.
So for the, is it the, they say propylamine? Is that how you say it? Propylamine?
Chris, can you try again? You're getting a lot of feedback for some reason. Maybe the mic was too close. I don't know. Can you try it again?
So working now, or is it sounds weird?
You sound weird again. Can you type it in? Or not? Or just try playing with your audio settings, okay? Try your audio and see if you can get it, and then ask in about 2 minutes, okay? Hydrogen bonds are really, really important in biological molecules. Extremely important because they hold together DNA, okay? And this shape here is called a, what? Anyone know?
Double helix.
Good. And this is a example of what's called an alpha helix in a protein, okay? And there's hydrogen bonds between them. And so we'll see this at the end of next semester, why they're very important. And the final force, and I think I'm going to stop after I talk about this. So I probably won't get all the way through, but I'll get most of the way through. If molecules are nonpolar, you might think that there's no attractions, right? Because it's like there's no positive, there's no negative. But even nonpolar molecules will have attractions. And that's because, remember what I said very early on today with MO theory? I said the electrons aren't necessarily stuck. the electrons can travel all over the molecule. And if they can travel all over the molecule, that means that sometimes they might build up on one side instead of another, if only very briefly. And if for an instant the electrons tend to build up on one side more than another, that side will be partially negative. So this molecule is pentane. We already talked about it a few minutes ago. We said it was nonpolar, totally nonpolar, zero dipole moment. But because the electrons can wander around, at one instant, this side might start to be negative. By the way, this normally would not be red. Normally, this whole thing should be green. But at one instant in time, since the electrons are wandering around, they might suddenly start to build up over here, and that would make this side negative. If all of a sudden these molecules get close to each other, and this is big negative, what's it going to do to these electrons? The electrons over here, do they want to be near those electrons? They generally don't. They repel each other. So these electrons get scared away over to this side. And in that fleeting instant, you have this side is more negative, this side is more positive. And what will they suddenly do? Since this is negative and this is positive, they will be attracted. But then these electrons come home. When they come back, what happens to this charge? It becomes plain old neutral again, right? And then these electrons go back, and then it's neutral again. And what happens to the attraction? It goes away. Yeah. So London dispersion forces there's two important words. First of all, they are temporary or fleeting, meaning they only last a very short amount of time. Only so long as the electrons wander from one side to another. This will be very important later in the class when we talk about bromine. Bromine is big. Its electrons like to wander around the molecule, okay, of Br2. So it's only so long as that happens. And the other important word is induce. Induce means like to compel. It's to force something to do something that it normally might not do. Normally, this molecule is neutral. The only reason it became positive is because this guy next to it got very negative. And when it was very negative, it kind of scared off the electrons for a second. So it became positive. This molecule induced a dipole next door. And as soon as the electrons come back and say, hey, there's nothing to be afraid of, it goes away again. Okay. They are generally weak. They are the weakest of the forces. But they become very important when molecules are huge. When molecules are long, that means that all of a sudden you can have all these little forces build up at once. And so for things like waxes, they are very important, okay? Waxes are long molecules of carbons and hydrogens like this. And the fleeting attractions are constantly changing. They're constantly moving around. So this means at any point in time, there's always going to be some place that's attracted, okay? And this gives us a good example for how this works with a gecko. If you ever see a gecko can stick to glass very easily. Geckos can climb up all kinds of surfaces. Now, I can't zoom in well enough to show you. Well, I can kind of zoom in. But if we were to take, I don't want to cut the gecko's toe off, but say you had a dead gecko and you were to look at these feet and under an electron microscope, you would see that they have large, huge surface areas, okay? It's like lots of long hairs and things like that. So what that means is it builds up lots of London forces because of these long molecules against the surface, and it will stick. Now, this would be bad if the gecko stuck and could never get unstuck, right? So because the forces are still weak enough, it can still pull out of those forces and move somewhere else. So it's very, very important because, again, they have many, many flexible hairs, and those all give lots of surface area. So what's the most important thing for London forces then? Molecules that have a lot of surface area. So molecules that are long and like a cylinder. I know that probably doesn't look like a cylinder to you, but we would call this cylindrical. Things that are long and round around them, so they can easily roll over each other. So, for example, look at these guys right here. Butane, pentane, hexane. Why in general, when we have not only more mass, why do we have a higher boiling point? Why are the boiling points getting bigger and bigger? Because they also have a bigger surface area, okay? They're longer, more surface area. More surface area means more points of attraction. Okay. In other words, if you were to draw this like a cylinder, you know, this would be a long, long cylinder. Floating on top of another long cylinder. And at any point in time, there might be an attraction here, 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 and then that attraction disappears. And now a new attraction appears here and here. So long as they're long like that, we get those kinds of attractions. This doesn't work very well for this compound. Which we talked about earlier today, very briefly, when we were drawing isomers. Because this one's not shaped like a cylinder, this one's shaped more like a sphere. It's got these little points sticking out of it. So not very much surface area means weak attractions. We'll talk about this again in chapter 4, because I'll come back to this same example in chapter 4. So if you don't remember them, that's fine. Okay, but generally, larger mass means higher boiling point and greater intermolecular forces. Those are the two things. So if the intermolecular forces are the same, usually the molecule with the greater mass is going to have the higher boiling point. What about water? Water is much tinier than any of these, but what's its boiling point? What temperature does water boil at? 100 C, good. So why is water so much greater than any of these? It's much smaller, but it can do what that these can't? It can
hydrogen bond,
and that's the strongest intermolecular force. So even though it's tiny, it has 4 places it can make hydrogen bonds, the 2 hydrogens and the 2 lone pairs. So each one of these waters can be attracted to 4 other waters. It's massive attractions, okay? Hexane only has very quick attractions that come and go. Okay.
Quick question.
Sure.
Looking at acetone up there, I mean, on paper it says the boiling point is 56.3, and you know, we know room temperature, but I mean, we also know that acetone's pretty volatile at room temperature.
Yes.
Because the intermolecular forces are weaker because it's only dipole-dipole and there's no hydrogen.
Yes. And if you think of air just blowing through the room, as air blows right across it, that's what we mean by volatile. Volatile has to do with the vapor pressure at the surface, right?
That's right.
So it doesn't take very much to separate them. Same with any of these. You know, these are, hexane is found, for example, in gasoline. Is gasoline volatile?
Yeah.
Oh yeah, big time. It means weak attractions, weak attractions at the surface. Any wind, any gust of air will liberate. It's enough energy to break those attractions at the surface. Boiling point means not just at the surface. That means the attractions all throughout the liquid, throughout the whole volume. But volatile typically means at the surface.
Vapor pressure. That's a good reminder too. Yeah.
Yeah. And we'll focus on that when we talk about distillation a lot. Okay. And so I already mentioned this. I'm sorry, I just did this a second ago, but branches basically are pokey. They minimize the surface area. More branching means less surface area. And so that does what to the attractions? It lowers them and makes the boiling point go
Down.
down. These are all, remember, what word did we use for all three of these? They're what to each other?
Isomers.
Isomers. Very good. Okay. I'm going to put solubility off to next week. We're not going to talk. I mean, it's not that much more. Now it'll take 5 minutes. 5 minutes, I promise. Okay. And we'll spend a lot of time on it anyway next week. Okay. Solubility, how well one compound dissolves in another. We're going to be interested in two types of solvents in this class, protic and aprotic, or typically we'll also say polar and nonpolar. Okay. They don't always, there is such thing as a polar aprotic solvent, but there's really no such thing as a protic solvent that's not polar. They're always polar. So things tend to mix when they have similar intermolecular forces. So these guys would all mix very well. They would be, pentane and hexane would mix, they would be very soluble in each other because they have similar intermolecular forces. What would not mix well with hexane at all? What is a very different molecule?
Water.
Water. Yeah, water and hexane do not go well together at all. So we say like dissolves like if they generally have similar intermolecular forces. So polar compounds generally mix well with other polar compounds. Nonpolar generally mix well with other nonpolar. If there's a big difference in size, that's why I've got the generally there. Then that might be a difference. You know, sometimes that doesn't work. But if you've got molecules of about the same size and about the same polarity, they tend to mix very well. The reason this becomes very important in some compounds like soaps, we find these kinds of molecules in soaps, is if you look at a soap molecule, it has two groups to it. It's got a long carbon-hydrogen chain, which is very nonpolar. On the other extreme, it's got two oxygens with lone pairs. This side is very polar. Anything with charges are even more extreme than hydrogen bonding. If you've got charges, like negative charges, they're going to be very attracted to positive charges. So very, very polar. We call this kind of a group hydrophilic, which means water-loving, and hydrophobic, which means either water-fearing or water-hating. Okay. When we want to clean something which is greasy, soaps are ideal for this because greasy things are what? Polar or nonpolar?
Nonpolar.
Nonpolar. But if you just put water on top of grease, that doesn't work very well. It doesn't break up the grease because it's not attracted to it. So soap molecules have to have both pieces. The nonpolar part helps to separate the nonpolar attractions between other molecules. The polar part will be attracted to water. So if you mix in all these soap molecules with grease, the grease will be attracted to the nonpolar group. And then the polar parts will be attracted to each other as well as water. So this is how soap basically works. Any grease gets stuck, bonded to what we are going to call the tails, these nonpolar tails. And they all like to bundle on the inside. So all the nonpolar on the inside, and then the polar groups like to clump together on the outside. Of course, where else do we see something very similar to this? In biology, where do we see it?
Lipids.
Yeah, the phospholipids, which are these cell membranes, right? Okay. The difference with cells are you don't have one layer, you have two, right? You have polar on the outside, nonpolar, non-polar, and then polar on the inside, because most of what's in a cell is usually water, right? So you have a bilayer. So we'll talk about that stuff later as well. So in any case, this is how this works for us in a practical application. All right. So again, nonpolars won't dissolve very well in water because there's not much attraction. By the way, like dissolves like, it doesn't mean that nonpolar doesn't like water. That's totally wrong. Gasoline would be attracted to water. That would be true, because you still have these forces. You saw these positives and negatives, and therefore they would be attracted to water. The problem is that the romance only goes one way. Water is totally uninterested in nonpolar, because what is water going to be? What is polar going to want to be with? It's always going to want to be with polar. And if nonpolars come along and say, well, look, I've got this negative charge, if only for a second. No, it's too weak, too small. So really what it is polar are very cliquey. They only want to be near other polars. And nonpolars, even though they're attracted to polars, it's just polar is not attracted back. So the consequence is that they stay separated. Okay, so it's not that the waters repel the nonpolar, it's because the waters are too attracted to other waters. Okay, they're already occupied. They have enough attractions already. Nonpolars are not interesting. Okay, and so that's what happens. Whenever you try to mix oil and water, they will briefly mix, and then the waters will all go off to their end and leave the oils off to their end, and they'll be satisfied with their weak attractions.